Hey, it's Mr. Beck, and I'm going to lead you through a derivation of the four equations of motion for constant acceleration. Now, the reason we're going to do this is you're going to see that it will make certain problems a lot easier. And I want you to see that these equations come from somewhere and aren't just kind of pulled out of thin air. So let's take a look as we move forward. Well, let's start with a sample problem. Here we have a car that starts at rest and accelerates to a speed of 25 meters per second as it covers a distance of 100 meters, and I want to know the magnitude of the car's acceleration. Well, that's kind of interesting. If we start identifying variables, we can see that the initial velocity is 0 meters per second because the car started at rest. We see the final velocity is 25 meters per second. That's the final speed. So I write that down as v is 25 meters per second. I know the distance is 100 meters, x, and what I'm looking for is the magnitude of the car's acceleration. Now, our equations so far don't give us the right thing to actually find that answer, because I know that acceleration is change in velocity over time, but I don't know what the time is. But what I do know is that my average velocity is my total distance traveled divided by the time. And so if I could know the average velocity and the distance, then I can get the time, and then I could plug that into the acceleration equation. Now, an average velocity, if I have constant acceleration, the average velocity is simply going to be the initial velocity plus the final velocity divided by 2, or 1/2 of v plus v0. So I can use that and plug in my final velocity and my initial velocity, which gives me an average velocity of 12.5 meters per second. Now, if I know that that average velocity is the distance traveled divided by the time, and I know that the distance traveled is 100 meters, now I can solve for the time. And so the time is going to be 100 meters divided by 12.5 meters per second, which gives me a time of 8 seconds. Now I can plug that into my acceleration equation, and so now I have my initial velocity, a final velocity, and time. So I can plug in 25 for my final velocity, 0 for my initial velocity, and 8 seconds for the time. And that gives me an acceleration of 3.125 meters per second squared. Now you'll notice we filled up a whole page with that problem, and so that final answer was a little bit more difficult to get to than I would like as I move ahead with physics. So in order to derive, we're going to start, we only have two equations so far. The equations we have are that average velocity is total distance traveled divided by total time. So we have an average velocity equation, that's great. The other equation we have is the equation for acceleration, or the average acceleration, which is going to be change in velocity divided by how much time goes by, or change in time. So we have average velocity, we have these two equations, but there's acceleration, velocity, distance, time, initial velocity, and final velocity. So not all the variables are showing up in each one of the equations. Change in distance is going to be my final position minus my initial position. Change in time is my final time minus my initial time. Acceleration is my final velocity minus my initial velocity, and change in time, of course, is my final time minus my initial time. To make things easier, what I'm going to do just for the purpose of this, I'm going to assume that we start off at a position of 0 and we start off at a time of 0. If we do that, then it'll make these equations just a little bit easier to step through. So I'm going to cross them out, and that simplifies these equations to be my average velocity is just my final x, my final position over time. My other assumption is that my average acceleration, if I'm constantly accelerating, which is where these equations work, then my initial acceleration, my final acceleration will be the same. So that's why we do this for constant acceleration. So now I've got a couple simpler things to do with my equations. So I can rewrite A average is V minus V0 over T minus T0. I can just write that as A is V minus V0 over T. So now I have this equation that I can work with, and I have this equation that I can work with, which is going to be easier. So now we're going to take that equation, and the first job is just going to be to rearrange that acceleration equation. If I take that and I multiply both sides by t, I wind up with at equals v minus v0. And then I can rearrange that and pull the v0 over by itself. And so I have v0 plus at if I move the v0 over to the other side. And then I'm going to rearrange one more time, and I'm going to get v is v0 plus at. This is the first of our 4 equations of motion. I've just rearranged the acceleration equation. I don't have any fractions anymore. But one thing that is important is that this is the first of our 4 equations of motion that we're going to use all the time. V equals V0 plus AT. It's just a rewriting of the acceleration equation. So our first equation of motion, there it is. V is V0 plus AT. Next, we're going to look at the average velocity equation. And if we look at that average velocity equation, what we're going to see is the average velocity is the distance traveled divided by how much time I have. And so I can write that again as the average velocity is also the initial velocity plus the final velocity divided by 2. For constant acceleration, I can just add them together and divide by 2 if you want to take an average. So now I can set those two equal to each other. So I can say that V0 plus V over 2 equals X over T. And now, that V0 plus V over 2 can be a half, and so I can have a half of V0 plus V equals X over T. My next step is I can multiply both sides by T. So I have 1/2 of V0 plus V times T equals X. And now I'm going to rearrange and put one on one side and one on the other side. So now I have X equals 1/2 of V0 plus V times T. That actually is my second equation of motion. So my position is half of V0 plus V times T. So the important thing is now you have 2 equations of motion. V is V0 plus AT, and X is 1/2 of V0 plus V times T. Now I'm going to combine some equations. What I'm going to do is I'm going to take this first equation of motion, V, and I'm going to plug it in to the second equation of motion. So I'm going to substitute the final velocity from the first equation into the second equation. So if I start with that second equation, which is 1/2 of V0 plus V times T, and I take that V, that V in the 1/2 V0 plus V times T, and I replace it with the V0 plus AT. Now what I've got is, well, V0 plus V0, of course, is 2V0. And then if I multiply through the half and I multiply through the T, what I wind up with is, multiply through by the T first. So the 2V0 becomes 2V0T, AT becomes AT squared. Now I can multiply through by the half. And when I multiply through by the half, I get, V0T plus 1/2 AT squared. So half of 2V0T is V0T, and half of AT squared is 1/2 AT squared. Well, that now is my third equation of motion for constant acceleration. Now we have one more combination of equations. What we're going to do is we're going to solve that first equation for T, and we're going to substitute it into the second equation. So that first equation, V equals V0 plus AT, I can solve for T, and that T is going to be V minus V0 over A. So subtract V0 from both sides, divide by A, and that gives you T. Now if I look at that second equation, 1/2 of V0 plus V times T, now I can plug in the T and substitute T for V minus V0 over A. If I multiply both sides by A and multiply both sides by 2, I wind up with 2AX equals V0 plus V times V minus V0. And if you remember your algebra and you have 2 terms like that, the way to combine those terms is to FOIL them. So first, outer, inner, last. So if I FOIL that right side of the equation, well, the firsts are going to be V0 times V. The outers are minus V0 squared. The inners are plus V squared. And the lasts are minus V0V. Now you'll notice there's a minus V0V and a plus V0V on the beginning and the end here. So they're actually going to disappear. So now I've got 2AX equals minus V0 squared plus V squared. So if I add V0 squared to both sides and then rearrange the equation, I wind up with V squared equals V0 squared plus 2AX. And that is my fourth equation of motion for constant acceleration. So here are 4 equations. Actually, 3 of them are on the official AP Physics equation sheet. The average velocity equation, the second one, actually is not there very handy, but those are our 4 equations of motion for constant acceleration. Now, why 4 equations? What the heck does this do for us? What this does for us is if I take those 4 equations, you'll notice that there are 5 variables that exist within those 4 equations. And those 5 variables are the position, the acceleration, the final velocity, the initial velocity, and time. If I look at the first equation, you'll notice that it does not have a position, but it does have the acceleration, the velocity, the initial velocity, and time. If I take a look at the second equation, it has the position, but it doesn't have the acceleration, but it does have the final velocity, initial velocity, and time. My third equation has the first 2 variables, but it's missing the final velocity. And my fourth equation has the first 4 variables, but it's missing time. So what's good about this is that there are 5 variables and there are 4 equations. In any problem, you're going to know 3 out of the 5 variables. So you're going to pick the equation that's missing the same variable that you're missing and you don't care about. So sometimes I like to say that the way to pick the equation is to figure out which variable you don't know and also that you don't care about, and pick the equation that also doesn't know about that variable and doesn't care about that variable. So how you pick the right equation? The proper answer is I don't know and I don't care. So now we can see, once we have these 4 equations, there are a lot of the equations of motion. There are a lot of problems that you'll see that you only need 1 equation. Occasionally you'll need 2 just to avoid like square rooting something, but very often you'll only need 1 of these 4 equations to solve just about any problem that we're going to do with equations of motion. So let's take a look back. This was our first problem that we did. Car starts at rest, accelerates to a speed of 25 meters per second, covers a distance of 100 meters, and we wanted the acceleration. And we had to do this page of physics work in order to get to that acceleration of 3.125 meters per second. However, let's take another look at this problem. Now again, we identified the variables. The car starts at rest, so that's an initial velocity of 0. Accelerates to a speed of 25 meters per second. You're going to have to be able to identify that as, oh, that's the final speed. So that's v equals 25 meters per second. But we have a distance of 100 meters, so I'm going to write that as x equals 100 meters. And I'm looking for the acceleration, so I'm looking for a equals question mark. So the 4 variables I'm interested in are initial velocity, final velocity, displacement, and acceleration. But I do not know time, and I do not care about time. So now what I'm going to do is look at my 4 equations and figure out which equation does not have time in it and does not care about time. And if I look at those 4 equations, the one without time in it, this one, is going to be this 4th equation of motion. This equation does not know about time. It does not care about time. So now if I move forward, what I can do is pick that equation and do some math. I can write that equation down. V squared is v0 squared plus 2ax. Substitute my variables. 25 squared equals 0 squared plus 2 times a times 100. Now I get to do some math. So I get 625, 0 squared of course goes away, equals 200a. And if I divide by 200, I wind up with a is 3.125 meters per second, which happens to be the same answer I got before. But you remember before it filled the whole page, and now I'm doing it in 3 lines. So this is the advantage of using these 4 equations of motion. I can do big, long, complicated problems, and I can do them in just a couple of lines.